This video is brought to you by Dev Mountain, a coding bootcamp that offers in-person and online courses in a variety of subjects including web development, iOS development, user experience design, software quality assurance, and Salesforce development. For more information, consult the link in the description below. It's going to be more or less the wrapping up of the mini-series that we have here on the iris classification model problem in Python. And just to kind of recap the previous two videos, first one, we just installed sklearn. We loaded up the iris dataset, explored it a little bit from a textual perspective, so just saw how that data was encoded from the dataset that was provided to us from sklearn. Part two, we elaborated a little bit on that from the graphical perspective, so we plotted some very simple scatter plots about the iris dataset with respect to the features, so how the features are interrelated for a given species of iris. And in this one, what we're going to be doing is we're going to be making use of leveraging a machine learning model from sklearn, in this case, the KNearest neighbors classifier model, which is going to be a built-in machine learning model that we can leverage with our data to determine whether or not a given species that we have not, let's say a given set of features that we have not seen before, what likely species this will be classified under. So this video is going to be more or less just kind of explaining roughly how the nearest neighbors classifier works. I think from an intuitive standpoint, it's a pretty straightforward algorithm. And the nice thing about sklearn is it just kind of provides the algorithm, the underlying features of all that to us. And it's very easy to leverage with just a very few lines of code. So we're going to be showing how to use that in this context, and then we're going to be running it and then also assessing the accuracy of this given model. So we might be able to leverage the nearest neighbors model itself for this particular data set, but how do we know how accurate it is? So we're going to go into a little bit of information about how we quantify the accuracy of a given model. So the goal really here is to use the what's known as the KNearest neighbors model to classify a given iris sample. And so generally, let me just kind of take the plot that we generated from the previous video over and explain a little bit about what this nearest neighbors problem is all about. So the nearest neighbors algorithm really finds the point in the set that we're given closest to the new point. So let me elaborate a little bit. Let's say that we have this data here, and each of these, again, like we had before, each of the colored dots corresponds to the samples that are categorized under one of the three species of iris. So this is the purple categorization. Doesn't really matter which one it corresponds to, the yellow and the green. And what we're plotting with respect to here is sepal length versus sepal width. And we can imagine that somebody gives us a set of features, a set of numbers essentially that correspond to each of the features. And that corresponds to a point somewhere on this graph. And the nearest neighbors problem is going to say, based on where this particular point falls in the graph, where does it likely fall with respect to classification? So for instance, if this new sample point fell somewhere in this region here, it's likely that it would be classified as a purple item because it's close to the other purple items. Likewise, if it's maybe somewhere around here next to these yellow items with respect to these two features that we're considering, it might be considered a species that corresponds to these yellow items here. So it's basically going to quantify how close it is to its neighbors, the neighbors being the other points in this set, this graph, and it's going to figure out how likely it is that any of the neighbors, let's just say like based on the neighbors that I'm close to, how likely is it that I'm one of these things based on the proximity that I am to these neighbors and based on how many of them happen to be of a particular type. So this it's called KNearest neighbors because we can quantify how many neighbors to consider. So for instance, if my new dot was here, I can consider the one closest neighbors, the two closest neighbors, the three closest neighbors, the K closest neighbors. So K is kind of a filler for how many neighbors I want to consider quantifying this point against. So if I'm here and I'm considering the first, let's say 5 closest points to this point over here, well, the 5 closest points are a purple one, so it's pretty likely that it's going to be purple. But however, maybe if I'm, let's say over here, and let's say this new sample plots somewhere over here, the 5 closest samples are 2 green and 3 yellow. Well, it could be a yellow, but it could also be a green. So it's a little bit hard to say based on that. So you can tweak the parameter there, the K parameter, based on how many neighbors you essentially want to consider within the closest proximity of the newest point that you're given in this graph. So that's the general idea of K closest neighbors. It's pretty intuitive. And so we also need to assess, after we do this, how to determine how well our model has performed. So we need to run it on data that it's not seen before. Specifically, that is, we need to run it on a new set of measurements and see where our model categorizes this new item. So to do this, what we're going to do is we're going to make use of some other functionality in sklearn, essentially that's going to allow us to split our data set up into two sets. And these two sets, let's say this practice, is very common in classification problems and other machine learning problems, where you split your data, your whole data, into two different sets. And one of them is called a training set, the other one is called a testing set. So one is going to be used to train our machine learning model. That's why it's called a training set. We're going to feed it to our machine learning model and have it sort of look at those examples and build use cases from that set that's given. And then we also want to we want to obscure some of that data from the machine learning model. So these are components of that set that it does not see. So if we have 150 records like we do from let's just go back to the Wikipedia page. If we have 150 records of iris samples, what we can do is we can split this set into, let's say, a 25 and 75% split, where 75% of the data is used to train our model, and then 25% we obscure from it. We know what the classification of those things are, so we know that, let's say that we obscure this particular entry from our machine learning model. The model doesn't know what this is, but we do, and we can ask the model, hey, given these features here, what do you think this actually corresponds to? And if our model says, oh, I think it's a setosa, that's one check mark for our model. It's sort of a bonus point for our model. It's gotten something right. So 25% of our data will keep from the training set, so that way we can actually test it on that. And if it's able to accurately classify the things that we know are one of these species, then we know that our model is going to probably perform pretty well on other types of, let's say, sets of feature data that we get from, let's say, a botanist or a biologist. So it's kind of the general gist of what we're doing there. So just to kind of reiterate that, we're going to be using the 75/25 split for the train test, respectively. So this is pretty typical. We'll use, our model is going to use 75% of the data, and then we're going to keep 25% for testing. So this is generally a common rule of thumb, let's say, where 75% is used for training and 25% is used for testing, but you can experiment with a split. A lot of it depends on how much data you can play with. A lot of it depends on how much data you have access to. So there's a lot of, let's just say, things that are beyond the scope of this video with respect to how you quantify that split. But for the sake of simplicity and for the sake of other examples that exist with respect to this data set that perform very well, we'll stick with a 75 and 25% split. So the nice thing about sklearn is it provides the ability for you to split the data with respect to training and testing. So what we can do is we can do the following thing. So we can say x train will create 4 variables: x underscore train, x underscore test, y underscore train, and y underscore test. And this is going to be equal to train, test, split. And this is a built-in function that's part of sklearn. And what we're going to do is we're going to give it what we're trying to, essentially our data. So what we want to split is the data. So we'll give it the data here. And then we also want to split, I guess the other component that this function takes, rather, is the target data. So what are we trying to predict? So let me just kind of unpack this and explain to you what exactly is going on here. And actually, what I need to do first is I need to import the train test split function from sklearn. So what I'm going to do is I'm going to say from sklearn dot model underscore selection, we're going to import the function train test split, which is the one that we just made use of here. So what's going on here? So this is a function that's provided to us from sklearn. It takes two things: the data that you want to actually run this model, that you actually want to split, and then the target. So what are you trying to predict? And it's going to return to you 4 objects. Now, the way in machine learning that you generally represent the data itself, so X, uppercase X, is usually denoted for the data, and then lowercase y is kind of the targets. So what we have here is we have 4 things. X train, that is the training set of data, so that's what's represented from this first variable here. X test, that is the part of the data, in this case, let's just say the 25% or so that we decide to obscure from our model, that's going to be stored in this variable X test. And then we also have a very similar thing, y underscore train. This is going to be the target content that corresponds to our training data, and then y underscore test, and that's going to be the target content of the stuff that we're obscuring, that we're trying to test our machine learning model on. And one thing that we can also add as an extra argument here is the random state. So basically the way that this function works is it's going to take the data that you give it and the targets that you give it, and it's going to randomly split them up into a train test split. And it's going to do that randomly every time you run this program. Now what I can do here with this random state optional parameter is I can set this equal to 0. So that's going to kind of allow us to do some reproducibility tests. So if you run this with random states equal to 0, you're going to get the same exact components from this particular data set in these variables. And this is good if you're trying to test some things out. It's kind of like a seed if you're familiar with generating random numbers or something along those lines. We're essentially setting the seed for the random split here to be equal to a number which is 0 in this case. So I hope that made sense. It's a bit long-winded, but this is going to give us, it's a very concise way of taking our data set and splitting it up into training and testing sets. And that's kind of what we have here. So the next thing that we can do is we can use something which is also quite concise, and we can make use of the KNearest neighbors classifier component, which is part of sklearn. So we're going to go ahead and import that as well. So I'm going to say from sklearn dot neighbors, and this is going to be import KN neighbors, so K neighbors I should say, classifier. So this is the function that's provided as part of sklearn that's going to allow us to just run this nearest neighbors classifier on the data, just like we kind of briefly described in the very beginning of this video. So if I go down here, I can say KNN, it's just a variable that we're just going to define, is equal to KNearest neighbors classifier. And what we can do here is we can set the a parameter which is going to dictate how many neighbors, what is our K value for what we're going to consider for a model. So this is denoted by n underscore neighbors. And what I can do is I can just set this, let's just say to 1 for simplicity. But again, this is an optional parameter where you can specify, given some sort of a sample that you don't know where it falls in the spectrum of species, you can consider other neighbors that it's close to. In this case, it's just considering the closest neighbor to that given sample. So that given sample has 4 numbers. You're considering what is the closest point to that particular point on this from the data that we have. So you can change that to a higher value, a lower value, well, not lower than 1, but you can change it to a higher value, and you can kind of experiment to see what you get. So that's going to build for us, it's all you need, it's going to build for us an object that we have here in KNN, which is the nearest neighbor classifier object, which has this, in this case, with respect to considering 1 neighbor. So what we can do then is we can call the fit function. So any object of this class that we're creating here is going to have access to a function which is called fit. So we're fitting our model with respect to some data. And what are we trying to fit it to? We're trying to fit it with respect to the training data. So I can say knn.fit, and I'll give it the training and testing data. Sorry, the training and, I should say the training data and the training targets. So this is X train, again, for the data set, and then Y train, which is the targets that we're trying to predict. So this is building our model. It's fitting the nearest neighbors model with respect to our training data. So it's taking that data and also the targets that are relative to those data sets. So then what I can do is, once we have our model, that's pretty much it. So our model is ready to go. So what I can do now is I can imagine that somebody has given me some new sample of iris data. So let's just call this x underscore new. And this is just equal to, let's say, a row. So the way that we're going to do this is we're going to define a row as a NumPy array. So I imagine you already have NumPy installed on your machine if you're running sklearn. I believe it is a dependency and it comes with it. If not, what you can do is you can navigate over to your terminal and you can type in pip install, and then you can say NumPy. So that'll go ahead and install NumPy. For me, I've already got it installed. It says requirement already satisfied. If you don't have it installed, it will go ahead and install it on your machine. So before I do this NumPy array definition, I'm going to go ahead and make sure that I have it imported. So I'm going to say import NumPy as NP. And again, this is just kind of a shorthand, just like we saw in part 2 of this series, where we did the same thing with matplotlib. So we're kind of using NP as a shorthand to access functions that are provided to us from NumPy. So going back down here, so we're defining a new set of data that we might get from someone. So we're going to define this as an array. Let me just go back to this array here. And let's say that somebody gives us an iris that they don't know what species it is, but it has, let's say, a sepal length of 5, a sepal width of 2.9 maybe, and then let's say a petal length of 1, and then let's say a petal width of 0.2. So this is just some data that we have collected out in the field. We don't know where this has come from, and we want to figure out, hey, what do you think this is? So if I go ahead and just print out x_new.shape, let's just see what we get. So let's just say Python part3, which is the name of this file. Print that out. Hopefully we should not see any errors. And it's just letting us know it's a list, or an array in this case, a NumPy array that has 4 components. So it's just the shape function. If you're not familiar in NumPy, is any NumPy array is going to have access to the .shape method, and it's going to let you know what is the dimension of the thing that you're trying to get the shape of in this case. I'm just going to get rid of that. So now what we want to do is we want to predict, we want to obtain a prediction of our new thing that we've obtained. We want to figure out, okay, what is, essentially, what do you think this particular sample is? Where would you classify it? Do you think it's the Setosa, the Virginica, the versicolor? What does the model think this particular thing is? So what we can do is we can define a variable, which is going to be called, in this case, prediction. This is equal to KNN, and again, we have access to a function from this KNN object that we've created up above called predict. So just like we use fit to fit our model with respect to the training data, we can predict the outcome of a given sample from this predict function. So I'm going to go ahead and predict what it thinks essentially the corresponding y, or the target of this data set is. So given this sample where we have 5, 2.9, and 1, and 0.2 for this given sample, what is the prediction that our model gives for this? So we can say print prediction. So if we do that, go ahead and run this, we should get a, let's see here, so I believe I left out, this should maybe be that, this should be this. Let's see if that actually works here. Let's see, I might be missing a comma, extra square bracket. So let me just wrap this in a square bracket, try this again, and let me go that. Okay, good. So what we have here is we have the prediction of the nearest neighbor's model that has given us a result of 0. So this particular sample that we've collected seems to think, our model seems to think, that this is the enumeration for whatever 0 is. So I believe 0 corresponds to the species Setosa. So our model is saying, I think, based on the data that you give me, that this is a Setosa species. Okay, well, how accurate is our model? So one of the things we can do is we can quantify how accurate our model is. And the way that we can do that is we can make use of the testing data that we've obscured from before in our train test split. And we can run our model, we can specifically run a function that the nearest neighbor's object is going to allow us to run, which is score. And that's going to allow, well, basically what's going on under the covers is it's going to look at the test data. It's going to use the model to make a prediction, just like we did for one of the sample that we got. And it's going to analyze whether or not the sample that, or let's say the outcome, the classification that it got, agrees with the Y test. So does the Y test, the testing component of what it's trying to predict, agree with what the model gave us? And then it's going to give us a score. So a score is going to be a value from 0 to 1, which is how accurate our model is on that particular testing set. So what we can do is we can go ahead and do this to see how accurate our model is. So we can say print, which is going to print out the result of the score, knn.score. So again, this is a built-in function that we have access to, and we can run this on x test and y_test. So again, as far as the model is concerned, it hasn't seen this. It doesn't know what the result of this is. We're feeding this information into this score function, and it's going to try to make a prediction using the model that we just created, and then it's going to match that up with Y test. It's going to say, did the model get the right answer? And if so, that's a green check mark. That's great. If not, it's going to put an X there. It's going to make that score lower. So let's just go ahead and we'll clear the terminal. So let's just say clear, and let's just say Python part3 just to see, oops, I didn't write the right file here. Still didn't do the right thing. Let me clear it again. Python part3.py. And in this case, we get a value from 0 to 1. In this case, it's quite high. It's about 97%. So with 97% accuracy, our model is able to predict the correct species of the test set of data. So again, it's operating on this kind of given 75% train, 25% test. So not so bad. And for a first pass, for a machine learning model that does something relatively sophisticated, this is pretty good. It's very concise with respect to the amount of code that you actually have to write. So that's pretty much it for this video. I just wanted to give kind of a first pass of how to kind of understand more or less the hello world application of machine learning, or at least one of them, which I think is the iris classification model. And this is just one of the models that you can build to classify some data that you're given. There's a lot more, of course. Machine learning is a very rich and deep topic, and I hope to make more videos about it. And in fact, if you found this particular series of videos useful, if you'd like to see more on this type of content, you can let me know, and I can try to plan some other maybe mini series or longer series on this type of thing. So let me know what you think. As always, the code will be provided on my GitHub. The link to that will be in the description below. If you have any comments or questions, don't hesitate to leave them in the comment section, and I'll catch you in the next series of videos.